list of choices, and so I am not necessarily going to do this the same way that's done in the solutions. That doesn't mean my way is better or that that the other way is better. It's just I do it the way I do it, and there's lots of different ways to do it. And the reason I do it the way I do is because I can't keep stuff in my head because it falls out, and so I can only keep a couple formulas at a time. And so all of those formulas that you have for power, they're really all the same. They all come from the same thing. And so I just remember a couple of them, and then everything else comes from that. So that's how I do almost all power problems. And you might not believe it, but they really do all come from just some basic stuff. And so the basic stuff is that you learned in Circuits 1 that power was voltage times current. And that's fine as long as you're in DC. If you are in AC, things start to change. The voltage is oscillating, the current is oscillating. So what do we mean by voltage? What do we mean by current? We have an average value that we use that we call root mean square. And for any sinusoid, the root mean square equals the peak voltage, which you know what that is because if you remember back from your trigonometry class in high school, the amplitude tells you what the peak value is. So that's the number, that's the phasor number, that's the magnitude for the phasor. You take that peak number, which is the magnitude, and divide it by the square root of 2. So the average value for your voltage or your current, which is oscillating, a type of average is this root mean square average, and it's the peak value divided by the square root of 2. Also, when we start dealing with AC, we put things in complex numbers because that lets us turn the sinusoids into phasors, which were a lot easier to deal with than the sinusoids because phasors just are easier to calculate with. So now we have a complex part. So now we have complex numbers. And so our complex power, we have a new symbol for it, and there's some sort of way you indicate that we're talking about the complex value and not the magnitude. The way Mr. Rabelais does is with the little squiggle. That's as good as any. A book usually will do it in bold. So that's saying that this is the complex value. The complex value equals 1/2 the max voltage, if I don't put RMS, I mean max, times the conjugate of the current. And that's the complex power. By conjugate, if you remember any complex number, a complex number looks like A plus JB. Its conjugate is A minus JB. You just change the sign of the imaginary part. If you have it written as a phasor, if I had the magnitude angle theta, then the conjugate would be the magnitude angle minus theta. You just change the sign of the angle. And so that's what we mean by conjugate. So one of the formulas I remember is this. Where does the 1/2 come from? It comes from the fact that if I multiply V times the square root of V over the square root of 2 times I over the square root of 2, I get VI over 2, or 1/2 VI. That's where the 1/2 comes from. That's why we have a 1/2 in the complex version and we don't in the DC version. So I remember that complex power is 1/2 the voltage times the conjugate of the current. These are both their complex values. Now, if I want just the magnitude of the power, so one way to say that you want the magnitude is to put it in those absolute values, or I can just write it without the little squiggly on top. If I just want the magnitude of it, that has a special name that's called apparent power. And that just means the magnitude. But once you have found the complex power, you have the magnitude. So you don't have to do a separate computation to find the apparent power. If you find the complex power, you've found all the powers. You found everything. So that's why I just find the complex power. No matter what the problem asks for, I find the complex power, and then I see what it asks for. because once I have the complex power, I have everything else, because the complex power also equals the real average power plus J times the reactive power. So P is the real power, also called average power. And it's the power that the resistors are using. Q is the reactive power. And that's the power the capacitors and the inductors are using. And Q is less than 0 for capacitors. And Q is greater than 0 for inductors. All right, so let's see. The only other thing that I'm going to do that's slightly different, yes.
Can you remind me again of the units for complex?
Oh, absolutely, yes. Excellent
reactive?
question. So complex power or apparent power are in volt amperes. Now, a volt ampere actually has the same base units as a watt. A watt is a unit of power. Power is energy per time. That's joules per second. That's kilograms meters squared per second squared. And a volt ampere has exactly the same base units. So it's not different units, but we call it different so that we know what we're talking about. So complex power and apparent power are volt amperes. Reactive power are volt amperes reactive, VAR, and power is in watts. The last thing that I do that is a little bit different, not different like worldwide, everybody does this worldwide, but it's not really focused on usually the book's problems. The book mentions it, but anyway, I find it very helpful. And it's called the power triangle. And with this, I can put together any last bit that I don't already have. And so the power triangle is the triangle that has apparent power on the hypotenuse, it has real power horizontal, and it has reactive power vertical, and it's a right triangle. And if you remember that, that tells you what you need to know about your power factor and that angle that shows up all over the place. So this angle, which is the current angle minus the voltage angle, it is also the impedance angle. So it's the angle whenever we're talking about the angle that goes with the power factor. The power factor is the cosine of that angle. And if you look at our right triangle, yes?
Isn't it the way around? It's the theta voltage minus the theta currents?
Is it? Somebody tell me. I don't.
Theta V minus theta
Is
I.
V minus I?
V minus I.
Yeah, because I has the conjugate, so it eventually changes the positives onto negatives.
This is an example of things that I say when I can't keep things in my head. This is an example. I tried to put something in here that I didn't have, and yeah, it messed it up. But I could have gotten to it with the stuff that I do remember. Okay, so V minus I. But I do know that the power factor is the cosine of theta, and the cosine of theta is P over S. It's the real power over the apparent power. Voltage. Right. Okay, so now with that, let's look at our problem. Okay. For the network below, determine the load impedance that will provide for maximum average power transfer. So, the other thing that you can't forget is that voltage equals current times impedance It's just the same as Ohm's law, but with impedance instead of resistance. And so with the things that I've written up there, you can answer all of the power questions, except for a shunt capacitor. There are a few formulas for shunt capacitors that it's a lot more handy just to use the formulas. It's the one thing that I'll tell you, just plug into the formula. Okay, so load impedance that will provide for maximum average power transfer. So maximum average power transfer will happen when you have minimized that reactive power, because the reactive power doesn't give you anything real. You want real power. And so to minimize the reactive power, you would like your load to have a reactive power that is the opposite of everything else in the circuit so that they'll cancel each other out. So you want Z load to be the conjugate of Z Thevenin. So you find Z Thevenin and then you change the sign of the imaginary, and that tells you the load impedance, that tells you what Z max is. So that would be Z max. Okay, so to find Z Thevenin, we're going to take a look at our circuit from the point of view of the load. For Thevenin, you short out voltage sources. If you had a current source, you would make that an open circuit. And here's our load, right here. So we need to find the equivalent impedance as seen by the load. So as seen by the load, that branch in the middle, the 50 minus J15, is in parallel with the 100, as seen by the load. Y'all see how that works in this one? And so this was 100, this is 50, this is minus J15. So I have 100 in parallel with 50 minus J15. So that equals 100 times 50 minus J15 over 100 plus 50 minus J15. And if you still don't have one of these calculators, you really should. If you have an 89 or an Inspire CAS, then sure, that's great too. 84s are just a little bit harder to work with, unless you have a really old 84. If you have an old 84, then you're fine. But the newer 84s just don't deal with the complex numbers as well. Okay, so we wanted to have 100 times, was it 50 minus J15?
Yes.
50 minus J15. Now I'm going to try to do some of this in my head. I believe that would be 150 minus J15.
Yeah.
We'll see if I'm too sleepy to even do that. It's possible. J15 equals, okay, and so in as a phasor, it's 34 angle minus 11. Somebody write this down and tell me, so when I minimize the calculator, I'll have it back. 34.63 angle minus 10.99. And as rectangular, it is, oh, this calculator, this is not exactly the same calculator as y'all have. Hold on, let me get it. I can get it from here. This is the European version, and for some reason, it really does not like to, it's not going to do it for me. It really just wants to have it in fractions. There we go. 33.99 minus J6.6. 33.99 minus J6. Okay, so y'all tell me those two numbers again. So the polar was
34.6 at angle of negative 11.
And the rectangular was
34 minus J6.6.
34 minus J6.6.
Yes.
Okay, so the The Z max, we have to remember the last step is to take the conjugate. Don't forget that last step. The Z max is 34 plus J 6.6 ohms. You can either write it like that, or you could write it 34.6 angle 11 degrees ohms. Either one of those. Did I write the wrong number?
No, I did.
Okay. Okay, questions? All right, so the next question says, what is the average power Pmax transferred to Zmax when it's installed? If I were taking this test, I would have written that formula down on my formula sheet and I'd have it. But I don't have that formula, but that's okay. It's really not any harder to just do it. And so I'm just gonna go ahead and do it, just in case it wasn't max power. And you'll see, okay, well, what if I just had to find the power through the load and it wasn't max? So it's the same thing. The max power is the power regardless. And so in order to find the power through the load, and even if I were to use the formula, I would need to have the voltage across that load, because the formula has the voltage in it, I think, the formula for max power. So I have to get the voltage across that load. So now that I'm looking at this, I know that this was 34 plus J.66. My voltage over here is 300. So the voltage on
J 6.6 on the line.
it, thank you, 6.6, thank you. And when I was doing this at home, I kept trying to make it 66. So the voltage over here, all of that voltage is the same because it's all in parallel. So what we have is a circuit that has a voltage source and a resistor and then an impedance over here. And this impedance is made up of the parallel of minus J15 plus 50 in parallel with our Z load. And this is just another resistor up here, and this was 300. So we can find our voltage by doing voltage division to find the V right there. And so voltage division, the way voltage division works is, if I want to find V load, I take my total V, which is 300, times the impedance of the part that I want the voltage over, which is minus J15 plus 50 in parallel with Z load, which I don't know what that is yet, over minus J15 plus 50 in parallel with Z load plus 100. So voltage division says take the impedance of the thing you want the voltage over and divide it by the total impedance. So now I need to get the this parallel. So I need to get minus J15 plus 50 times 34 plus J 6.6 over minus J15 plus 50 plus 34 plus J 6.6. And now when I did this earlier, when I'd had a little bit of sleep, I did the addition on the bottom, by myself, but now I don't trust myself to even do that. Okay, whenever you multiply complex numbers or divide, don't forget to use parentheses. If you don't use parentheses, it's just going to do the operation on the J part, or perhaps just on the angle, so always use parentheses. So this was 34 plus J 6.6 times minus J15 plus 50 over, okay, I'm gonna live dangerously, 84
Yes.
minus 7.4? 8.4, okay, all right. That's just the sum, that's just everything added up. And I get 21.4 angle negative 0.03003. So 21.4 angle negative 0.003. The reason it's such a small angle is, do you remember how we found Zmax?
It was the complement.
It was the complement. Now, if we didn't have, we're not finding the Zmax with Z Thevenin, but most of it is there. The only thing that's not there is that little 100 ohm resistor, and so our angle is real close to 0. And our imaginary part will be real close to 0 too. So if I change this to rectangular, it's practically 0, 21.4 minus J.001. And this would be volts. Okay, so I'm just going to ignore that imaginary part when I do my next calculation. So my next calculation was, let's see, that was to find the voltage. Okay, and I'm supposed to find the maximum power. So I want power, complex power, equals 1/2 times the complex voltage times the conjugate of the current. Are you curious about what I just found?
Wait, I thought that was the parallel resistance.
That was the parallel resistance, and I haven't found the voltage yet.
Okay,
Right.
you put volt on the end of it.
I
so-
did, because I was wrong, and I was
Okay.
pretending now like I was planning this all along. So yes, so yeah. So thank you for yeah. It's this is an ohms of ohms. Okay, so 21.4. So this will be 300 times 21.4 over 121.4. So I was wrong earlier when I said the 100 ohms was not making, it's the other part that's not making I don't know what I'm talking about. All right, so this is going to be our voltage. So 300 times 21.4 over, I don't think y'all need to see me do that. 21.4 over 121.4, 52.88. And this will be angle 0. About angle 0, angle 0.001. And I think he did find this on the solutions. This is like something we can check and see. That does seem familiar. Okay, so now to find the current is always, you can always use Ohm's law. So if V equals the current times the impedance, the current equals V over the impedance. We just found the V is 52.88. Angle 0. Our impedance is 21.4. Angle negative 0.003. That's still going to end up with almost no angle. 2.47 angle almost 0. Amps. So it says conjugate, but if this is plus 0J, 2.47 plus 0J is the same as 2.47 minus 0J. That's what this little star means, is you change the sign of the imaginary part. So our complex power equals 1/2 times our voltage, which we got to be 52.88. And 2.47. I think that's right. Okay, and did somebody do this already? No?
65.3068.
Is that the right answer?
Well, his answer is, I don't want to say it's wrong, but he rounds very weirdly. Like, even if you do it his way, you're not going to get the exact answer he got.
Let's see.
I think his calculator's an actual fossil.
Yeah,
That's probably most of it.
I don't know why.
I
Yeah,
saw
he,
it.
like, his work is very,
No, so I have something wrong. Did you divide by 2? Did you divide by 2?
Mm-hmm.
Because I got the same answer he got earlier. Let's see, what did I do wrong?
11? I mean, that's pretty close.
I was gonna say, whenever you find the current, should you use the total impedance instead of just the parallel impedance?
No, because we're looking for the
Yes,
transfer.
yes, yes,
the
yes, yes,
element.
thank you, yes. Okay, so what I just found was, in case you wanted to know what the power was through all of that over there on the other side, that's what we just found. We found the power for everything, because I used the parallel impedance, so I used the impedance of all of this. So we just found that because we needed to know that for something. I don't know what, but yeah, okay, so there it is. But now let's get the power just through the load. And so the power just through the load, we need the current just through the load. So the current just through the load is the voltage, which was in volts and not ohms, 52.88. Divided by our impedance, and that's the impedance we found, 34 minus J 6.6. And now we will be taking the conjugate of this because this will have an angle. So this is 52 point, did I do something wrong?
I thought it was plus, you said minus.
No, because above we found the conjugate of the.
No, Zmax, no, it's correct, it needs to be a plus. Yeah, no, it's plus, because
Oh, but it will be after we.
I will be conjugating it again, and then it'll turn into minus. So this is, so let me just write down for those of you who didn't follow what we were all just talking about. This is I equals the voltage that we found, so this is the voltage we got by doing voltage division, over Z max. And Z max was our answer to part A.
Excuse me, Mr. Rep.
Yes.
For the Z, why wouldn't we use the parallel added with the 100?
Okay, I'll answer that as soon as I write this number down.
We're looking for the power through the load. And if we use the parallel one, we have the power through the whole right side.
Yeah, so, but he actually asked about even adding the resistor. Okay, so let's take a look at this circuit. So what are the sorts of things we could find the power? What are the sorts of things we could find the power of? So we could find,
Total parallel.
yep, so we could find And he could ask any of these things. You don't know what he's going to ask. He could ask for the power through the load, which is what he did ask. And when he asked for the power through the load, I need to find the voltage across the load, and depending on what formula I use, the current through just the load. If he had asked about the power for this part of it, then that's what I found just a minute ago, completely on purpose. And that, so I would use the impedance of that combined. If it asked for the entire power supplied by the voltage source, I could either find the power of the voltage source, or if for some reason I didn't know something about that, I didn't have the information for the voltage or the current, I could find the power of everything else, and that would be, everything else would be absorbing, and the power supply would be supplying. And so I don't know who asked the question about why I didn't add in the resistor. The reason why is because if it had asked for what is the entire power consumed by the circuit, then you add everything up. But the specific question is asking average power Pmax transferred to Zmax, and Zmax is just that right-hand part. Okay, so we were somewhere. It was, oh, and I didn't write down the angle. It was 1.52 angle negative 11. Okay, so that is the current through Zmax. So the complex voltage will equal the 1/2 the voltage times the conjugate of the current, which will be 1/2 times 52.88 times 1.52 angle positive 11. And by the way, in case you just are like me and anytime you enter a number into a calculator, you stand a chance of doing it wrong. So like if this is what I did on this calculator, 52.88 over 34 plus J 6.6, and that's my current. And I try to like retype as little as possible. So I want my voltage, which was 52.88 times the conjugate of that current. So I can do second complex conjugate, and I can either go up and copy it or just do second answer and then do that, and then that way I won't necessarily make a mistake. Is that the
Divide by 2.
divide by 2? And we get 40.36 angle 11.
It's. Wait till this might get knocked out the way this thing
I can check that.
Whenever
I mean, it's really close.
because
I mean,
it's all ballpark. Whenever I did his method,
I think that's why he like cares about.
Oh, it's if you do it correctly by any method, it is the same answer. It's just a matter of rounding. And like I rounded to 1 decimal place here and kept 5 over here, you know, and so it's like
although whenever
it really should come out the same.
because I did it the way he did it, and then also got
I did it both ways.
I got 39.62.
I got.
I mean, it's pretty close to.
I got 39.67.
I think I worked
41 and 11.
Okay.
41 angle 11. I think you started.
But like, how lenient do you think he is when it comes to these like rounding things?
If you show all your
Rounding, yeah, if you show all your work and it's correct, the rounding is not going to be a big deal.
Yeah, I think that's why he
Oh,
cares
yeah,
about
he-
work
yeah,
so
he-
much
Wait, is
because.
this part B or part C?
This is part C.
Oh, part C.
This is
okay.
part C.
Okay, just making sure.
Yeah.
Yeah. Okay.
It's
That
part
one-
C.
That checks out. I'm so smart. Yeah, that's what I got.
It's part C, yeah. We already did part B. Part B was,
2.7 milliamps.
Well, it was asking for average power, so I don't think it was an answer.
the load impedance,
Oh, no.
which was
I'm thinking of different
34.6.
I don't think. Well, no, that was part A.
Oh, that was part A. Oh, I know, I did C. I haven't gotten to B yet because I always find
Oh, yeah.
complex first. Always find complex first, because part B asks for average power. So this is complex power. Once I have complex power, I have everything, because all I need to do is put it in rectangular. So second complex, put in rectangular, and I get 39.62 plus J 7.69. 39.3 plus J 7.69. So 39.3 plus J 7.69 is the complex power in polar form. Now that I have that, it's easy. Real power is 39.3 watts. If it asked for reactive power, it'd be 7.9 VAR.
I see what you did.
You see what I did?
Yeah, I see why you went to.
That's
to
why
complex,
I
because-
always do it that way. I always do complex, and then I have everything and I'm done.
Gotcha.
And so it's not the same way that a lot of people do it, but I just can't keep all those formulas straight. And this way always works. I mean, there's all those other formulas are based on this. And so now, except, okay, so, sorry, the maximum average power does have its own formula. So I just found the power, and it happened to be the maximum power because we had the maximum impedance. But there is a formula, once you know what Z max is, there is a formula for maximum power that has an 8 in it somewhere.
Yeah,
That I don't have my formula sheet with me, so it wasn't the way I was planning to do it, but you can, what is it?
It's 1/8 V, absolute value VS squared over R. Or
VS.
V squared over R.
V squared over R. Okay, so one of the reasons that I don't, thank you.
Let's see.
Yeah, one of the reasons that I avoid using these is because people get confused about what does this mean. And so this means the magnitude of V. So it just means just the magnitude, and R means just the real part of the impedance. And so using this formula works just fine, and it's plenty easy, but you have to remember what all of those things are. And the magnitude of VS squared is not exactly the same as VS squared. The way magnitude, if you take the magnitude of a complex number and square it, what that is the complex number times its conjugate. And so if you take the complex number and square it, what you get is the magnitude, and the angle is twice as much as the original angle, but if you multiply it times its conjugate, it gets rid of the angle and you have a real number. So anyway, okay, so there's that. Were there any other questions that went with this problem?
So for that, we would be using the voltage, we calculated from doing the voltage division part
Yes,
of-
you'd
okay.
still be using the voltage across that thingy.
Yep.
Yeah. Okay.
Are you talking about for the
For part,
for part B?
for parts, the part of part B that we did in part C. The,
You're always
the
going to
other
use
one.
the voltage
Yeah.
across the load if we're looking for something across the load.
Gotcha. Yeah,
For using the
that would
maximum,
make sense.
for using the max average power equation.
Yeah.
Okay, so
use the Thevenin, V Thevenin.
Oh, okay.
You use what and those use what
Got it.
what is the question?
for the voltage divisions. Part B, you don't use the load, and
Yeah.
part C, you do.
Yeah.
Yeah.
Oh,
'cause
I don't do it with oh, yeah, that's
Yeah.
right, you do. You use the Thevenin voltage.
Yeah, because
Yeah.
you already calculated the Thevenin.
You do use the
resistor,
Thevenin voltage.
And you need to
Yeah,
match
okay, so yeah, it is the I forgot all about that. That is the Thevenin voltage. Another reason not to use that formula. I mean, because I mean, seriously, if you have all that stuff, go ahead. There's nothing wrong with it. But you have to remember that that formula, that's the Thevenin voltage. So this is the Thevenin voltage. And it's the magnitude of the Thevenin voltage squared. This is just the resistance, just the real part of the resistance. Whereas if you just use the plain old power formula, you don't have to.
You can find the other power.
You can find the other
Yeah,
stuff.
That makes sense.
But I mean, if all you had was this, then yes. And it's not nothing. There's not. It's nothing wrong with it. It's just it's me. I can't remember these things, so I just stick with what I can remember. Okay. All right. Let's take a look at the next one. And then I'm gonna have to go to my Greek class. Okay. And I won't be able to do. I will do the Bodhi plot. It's real quick. I might actually have time to do it. Who was the person who said anything but Bodhi plots?
Like I got Bodhi plus, yeah.
Okay. The apparent power entering a certain load, so apparent power, that's S, and it's the magnitude of our complex voltage. So we don't know the real part, we don't know the imaginary part, but we know the magnitude is 250 VA. At a power factor of 0.8 leading. Now I know everything. Here's how I know everything. Because this is 250, and I know the cosine of this angle is 0.8. So the cosine of theta is 0.8. The cosine of theta is also P over 250. P over 250 equals 0.8, or P equals 200?
Wait. I think you times it, but okay. Yeah, makes sense.
It's 50, and that would make Q 150. So it's just right triangle, just a right triangle. So I now know my real power, so I now know my complex power. Like I said, I always find my complex power. It just gives me comfort. So here we have 200 plus J 150 is my complex power. Okay, now it's asking for the RMS current magnitude into the load. All right, so I have the voltage magnitude across the load. VL is 125 V, and it's telling me it's RMS. That's important, at 1 megahertz. Okay, so I know, and that is just the magnitude, so I do not know, I do know the angle, let's see.
I don't think
I know theta, I can find theta, I know, let me figure out how I want to do it, and then I will take y'all's suggestions. So, I would say,
Insane, honestly.
okay, so it is true that if we take, if you take the complex power and say it's the complex voltage times the conjugate of the current, then the apparent power does equal the magnitude of the voltage times the magnitude of the current. There's not a 1/2 here because our V is already in RMS. And so our apparent magnitude was 250 equals 125 times I, and this would be RMS. and I RMS equals 2 amps. Now that's just the magnitude. So does anybody who was like raising their hand a minute ago still have, yes?
The imaginary part's supposed to be negative because it's leading.
The imaginary part is supposed to be negative because it is leading. So that was the other thing that I didn't put on that front sheet, which is the last piece of information that you need to know besides the things that I told you, is that this part right here, you don't know if that's plus or minus until they tell you, because the inverse cosine of 0.8 gives you a positive number on the calculator, but the negative angle has the exact same cosine. And so whether you have a plus or minus here depends on whether it's leading or lagging. So if it's leading, then you have minus. If it's lagging, then you have plus. Or the other way you can know is if they tell you it's capacitive or inductive. So capacitive is negative, inductive is positive. Thank you so much for that correction. Let this be a warning to you when you ever decide to do what I do. Don't leave your notes at home, or make sure you have a class full of people that know all the answers, and that's helpful too. Okay, all right. So this should have been a minus, and does everybody understand how we knew that? Because it said leading. So because that part we don't know. All right. Now it says determine S. Did we already determine S through the load?
Yeah, you did that one. That is the complex power.
Okay,
So that was the
all right.
first thing.
Now determine the value of Z load. Okay, so we know that we have, so the angle for the this angle that we found in our triangle is the angle for the impedance. And so if I take the inverse cosine of 0.8, it's 40 something, right?
Negative, or it's
Yeah, well,
36.8.
36.8. And so, but we need the negative one because it's leading. And so theta is negative 36.8. Now we can get the magnitude with V equals IZ. So Z equals V over I. And V was 125. And I was 2. And that's 62.5, angle negative 36.8 degrees ohms.
How did you get that angle to be negative?
Leading.
Oh yeah, you're
It's-
right.
Oh, okay. Right, yeah, that just came right.
Yeah, so when I say leading, so that's also all of this leading, negative, capacitive. This is also the angle for the impedance. So that theta, so once you find it, it is also the angle for the impedance. And then it is the voltage minus current. Do you have a question?
Since if we know it's leading, does that also tell us that it's gonna have a negative on the voltage?
No, well, likely, we know that voltage theta is the angle of the voltage minus, do I have that right this time?
Yes.
Yes.
Yeah.
Yes.
And so if this is negative, well, we don't know for sure, no.
Okay,
Yeah.
and my other question is, how did you know, that it was gonna give you the magnitude of the impedance? Because this is how I did it too, but I ended up getting the magnitude.
Because I only used magnitudes.
Okay, yeah, that makes sense.
Okay, so So it is true that while I prefer to deal with the complex numbers in this problem, I didn't have them. And so I had to deal with magnitudes. So it is true that the magnitude of the apparent power equals 1/2 the magnitude of the voltage times the magnitude of the current. That is true. Or if it was RMS, the magnitude RMS and I RMS. I assume y'all have classes, or you just don't like me? Okay. So that was the answer. And also, V equals IZ is true both with the complex numbers and as well with magnitudes. Because anytime you're multiplying, you're just multiplying magnitudes and the angles add. Okay, and then we had ZL should be in the form R plus J omega L, or minus R minus J over 1 omega C. So we already know it's minus omega C because it's negative, so it's capacitive. So the first thing we need to do is change this to rectangular, and we get, in rectangular, we get 62.5 angle negative 36.8. In rectangular is 50.04 minus J 37.4.
I'm sorry, how did you do that?
I changed this to rectangular, and so I just did that on my calculator. And so that tells me that 37.4 equals 1 over omega C. Now I'm told my frequency is 1 megahertz. That hertz is key. That is not angular frequency. If it's in hertz, it's F. So F is 1 million hertz. So when they give it to you in hertz, that's F. If they give it to you in radians per second, that's angular frequency. If they don't put anything on it at all, that's angular. But if they say hertz, that's frequency. And omega, so this is something else you do have to know. Omega is 2 pi F. So 37.4 equals 1 over 2 pi times 10 to the 6 times C, or C equals 1 over 37.4 times 2 pi times 10 to the 6, which is a tiny little number, which I would be worried about, except I remember finding a tiny little number earlier.
26.6. No? Did I do something wrong?
I forgot about the 2 pies.
It's a 4 nano.
Oh, by the way, if you're using one of these calculators, it's a very rare I'm going to have a criticism. So I just did this, and it tells me 0.00004. It's not exactly that. What you have to, and even if I go up and highlight it and put it on the line below, yes.
Second mode, and you can change it to engineering notation.
Well, you can do that too. That's extra fancy. Darn it, I like that way better. Okay, but
sorry,
but it does happen like in physics too. If you need to find out what the other decimal places are, just after you do your answer, just multiply by 10 to the 9th, and it'll know it didn't work. Darn it. So when I do the calculation, I can multiply it by 10 to the 9th, or we'll put it in engineering mode. Okay, so all right. So what we do, you go to mode and engineering.
You're gonna have to do it again.
Yeah, I didn't even do the calculation on it on this calculator. What was the calculation? It was
1 over 37.4 times 2 pi times a million.
Does this calculator let me do 2 pi e to the, because the 84 does not. It does.
Yeah, that's right.
Okay, so 4.26 nano farads were a capacitor.
Oh,
4.26
Yeah, that's-
nanofarads.
9? Yeah.
All right, so quickly, I'm gonna do the Bodie plot because I have to go to class. But it's quick, but I don't have time to like explain everything in detail. So this is like kind of assuming you already know stuff. I'd prefer if you don't want to watch the Bodie plot, if you're gonna get up and leave, please do so quietly and quickly because I am trying to get out of here. So just yeah. So. You have an excuse because I know you have a hatred of them.
No, I didn't. No, I already know how to do it.
Yeah. Okay. So first of all, this one is already in the correct form. How do I know it's already in the correct form? All the things in my parentheses have ones. They start with ones. So I'm not going to talk about if it wasn't in correct form because I'm just going to do this quickly. I have my constant. My constant is 0.25. So I take 20 log 0.25, and if I believe that's like a negative 12 something,
Yeah.
Just about.
It's just right.
just about negative 12. So I put a horizontal line at negative 12. I always do my things through the origin next because the things through the origin are where I end up having problems because everything else is 0 until the corner frequency. The things through the origin are not. So I have a pole through the origin. Things through the origin go through 1. Go through 1. If they're zeros, they have positive slopes. If they're poles, they have negative slopes. The slope is going to be a multiple of 20. It's omega, so it's just negative 20. If it was omega squared, it'd be negative 40. Omega cubed would be negative 60. It's negative because it's a pole. It's a pole because it's in the denominator. To make it have a slope of negative 20, I go over, and then I go to the same type of vertical line in the next decade, and I put my dot there. So I'm going over 1 decade, so over to the same kind of vertical line, which is the one with the big space in front of it, and I go down 20. So this one is my constant. This is pole through origin. Next, I have something in the numerator. That's going to be a simple 0. A simple 0 has a corner frequency of whatever is underneath that omega. It's a 3. So it will be 0 until I get to 3. And the way you read a logarithmic plot is these vertical lines are at powers of 10. So when I go to 1, the next line is 2, 3, 4, 5, 6, 7, 8, 9, 10. And when I get to 10, it then goes by 20, 30, 40, 50, 60, 70, 80, 100. And then at 100, it goes 100, 200, 300, 400, and so forth. So if I want to get to 3, I start at 1, I go over to 3. So it's 0 until it gets to 3. And then it has a slope of plus 20. So I go over to the next decade to the same type of vertical line. So it's after the big space and then over 1 more to that. And then I go up 20 because it's a 0, so that's a positive slope. Slope of 20. And then I have my denominator has a pole at 100. So it's a pole, so there'll be a slope of negative 20. It's not squared, so it's just plain negative 20, not negative 40. So I'll go to 100, and it'll be 0 until I get to 100. And then after that, it will have a slope of negative 20. So I'll go over and down 20. And now to get my composite, I will go to this axis and I'll add together my numbers that are here. my numbers are 20, 0, and negative 12. The 20 came from the pole through the origin. If you have a pole or a 0 through the origin, that's going to give you a 20 or a negative 20, or if it's squared, a 40 or a negative 40. So I have a plus 20 and a minus 12, which gets me a plus 8. So that means I start at a positive 8. And then from here on out, I'm going to be adding slopes. There's no slope until I get to 3. Once I get to 3, I have a slope of plus 20. So I lied. I have a slope. I have a slope. I have a slope of minus 20. I have a slope of minus 20. So I start at 8, and then I have a slope of minus 20. So I'm at 8. I need to go down 20. 20 down from 8 is negative 12. So when I get over here, down 20 will be at negative 12. And then I keep going with that slope until I get to my 3 line, my 3 vertical line. So my 3 vertical line ends up being right about at negative 20. Now, once I get to 3, I now have a slope of negative 20 and a slope of positive 20. I told you this things through the origin messed me up. So a slope of negative 20, slope of positive 20 cancels out, and I have a slope of 0. So now I'm just happily moving along horizontally until I get to this pole. When I get to that pole, I have a slope of negative 20, and so I'll just go parallel to that line right there. And this is my composite. That says composite. This one was simple pole, and this one was simple 0. Okay, that's all I can do because I have to go. And we'll have our comprehensive review tomorrow. I will be repeating some of the same stuff I said here. If you didn't sign this, please do on your way out. Thank you so much for coming.